is back. So we're going to have a three-part tutorial on a lecture on probabilistic and combinatorial methods in coding theory by Jonathan Mosheiff, and this is part 1, and parts 2 and 3 will be tomorrow. Thank you.
Okay, hi everyone. So probabilistic and combinatorial methods. So what are we going to talk about? There's lots of things I want to tell you, and if we have time, we'll get to more than just what I'm going to outline here, but at least we're going to do what I'm going to do here. So the questions we're going to be talking about are going to be combinatorial, which means that they're not algorithmic. We're not going to we're not going to prove anything about complexity of decoding or questions like that. The sort of questions that we will be trying to answer is whether certain codes are list decodable or list recoverable up to some parameters in the combinatorial sense. So an example motivation is the question of how list decodable and how list recoverable are Reed-Solomon codes, okay? Up to what radius can we, for example, list decode a Reed-Solomon code? Again, not algorithmically yet, just in the combinatorial sense, in the information theory sense. I put this icon here because this involves certain open problems. Like some of this has been recently solved, but a lot of this still remains open. And we'll see what it was. And the star player in these talks is actually going to be the humble random linear code. So random linear code is a very, very basic construct. We're going to define exactly what we mean by random linear code soon. And maybe, in a sense, the technique that a lot of what we're going to do involves is first getting some understanding about what a random linear code does, how a random linear code behaves, and then reducing from a random linear code to more structured code. So we'll see, for example, how we can infer something about the behavior of Reed-Solomon codes, which are very interesting to us because they are structured and have some nice algorithms and very important. How we can use things we know about a random linear code and infer from them about these more structured and sophisticated codes. Okay, so this is going to be the main technique that we'll be exploring. And really, in this first talk, I think most of what we'll have time to do is to concentrate solely on random linear codes themselves. And as we progress, we'll be able to see how our knowledge of random linear codes can be used towards other more complicated code themselves. Okay, so let's define the basic combinatorial notions that we care about. So we know what's list decoding. I'll just say it quickly. Right, so unique decoding, we say that the code is row unique decodable. If given row and arrows, the receiver can always uniquely recover a code word. So in other words, we need there not to be, if our code is in FQ to the n, we need to avoid having a ball in FQ to the n that contains 2 or more code words. Okay, ball of radius row. In list decoding, we relax this, the unique decoding requirement, and we only want the receiver to be able to recover some list of possible code words of size at most L. So we allow, say, 2 code words in a ball, but we don't want there to be more than L. Okay? So if no ball contains more than L code words, we say that the code is list decodable with parameters row and L. And again, we don't care right now about how the receiver is going to algorithmically find these code words. We just care that the list itself is small. Then we also have list recovery. So in list decoding, we care about Hamming balls. We want Hamming balls not to have too many code words. In list recovery, we care instead about combinatorial rectangles. So we want every combinatorial rectangle in FQ to the n not to contain too many code words. And formally, we say that the code in FQ to the n is list recoverable with input list size little l and output list size big L, if the following holds. For every set of letters for each coordinate, okay, so we call them S1 to Sn, and these are going to be little l letters for each coordinate. The product of these sets S1 to Sn, that's called the combinatorial rectangle. Okay, so that would be all the words that fall within the given input list in each coordinate. And we want the intersection of the code with such a combinatorial rectangle not to be too large. We want it to contain at most, again, big L code words. And if this holds for every combinatorial rectangle, we say that the code is little l, big L is recoverable. Okay. Okay. And now to our star player, the random linear code, which is most of what we'll be talking about this hour. Okay. So random linear code is just a uniformly sampled linear subspace of dimension Rn in FQ. And one of the reasons we like random linear codes is that this is the go-to code for existing proofs. Usually, if we want to know whether there exists a code with a certain combinatorial property, it usually makes sense to first ask, is it true that a random linear code has this property? And sometimes even this leads to very complicated questions. So fully understanding or almost fully understanding list decodability of random linear codes, I think we can say that right now we really answered almost every question about list decodability of random linear codes. But this is like rather very, very new stuff, and it's been there's been many papers about this, and we still don't fully understand list recoverability of random linear code. Okay, so even these are tough questions, but still sometimes they're easier to answer for random linear code than for certain, more structured cases. Okay. Yeah. So things that we do know about random linear codes is that they achieve the Gilbert-Varshamov bound, and they also achieve what I call this is not a standard notion, but what I call the list decoding GV bound. In a sense, they are as list decodable as plain random code. So what does that mean? It means that if I want to list decode, sorry, this should be, this probably be a row. If I want to list decode up to some radius delta with list size L, then 1 minus h cubed delta is the gap is the capacity, and I can take if I go within a factor of 1 over L from the gap to capacity, I should be able to do that with random linear code. Okay, so any code satisfying this, you don't really like if these parameters don't sit well with you right now, you can forget about them. It's not like this specific trade-off is not very important, but there is this trade-off called the list decoding GV bound, and if a code achieves that, it's in a sense it achieves what we believe to be optimal list decodability. Yes.
What do you mean GV bound? It's an existence bound. There exists a code that has that property.
Yeah, and these are in a sense the best that we know to exist. So I mean. So that would be like the analog of achieving. That's why I call the list decoding GV bound, because that's the analog of achieving the Varshamov bound. Actually, Henry raised a very important point. Please ask questions. Okay, it would be really helpful if you do. And there are also many list recovery results about random linear codes. Again, we don't fully understand, but we do know that they do rather well with regard to list recoverability. Okay, so these codes are great. What's bad with them? What's bad with them is that they're not structured, and so algorithmically we can't do anything. Okay? So decoding them is almost certainly a hard problem. Certifying the properties on the left is almost certainly a hard problem. Okay, so given a random linear code, I want to prove that it's, I want to check whether it actually achieves the Gilbert-Varshamov bound. I don't know how to do that. And constructing them is it's a random process. It takes around n squared random bits if I want to construct a random linear code in F2. Why? Because I need to generate either a random generating matrix or a random parity check matrix, and each of these would have order of n squared bits. Okay, so this is the good and the bad about random linear codes. Yes?
Putting GV bound. This is for random linear codes or for random codes?
What, sorry?
This is putting GV bound. Yes.
So random linear codes achieve this.
With the 1 over L dependence?
No?
Yeah.
Sorry?
With the 1 over L dependence?
Didn't you show that? Like for a large cube?
Yeah, exactly.
No, for small cube, this was already known.
Oh, I guess there's an intermediate gap.
Yeah, that's why I said, okay, yeah, so this is like almost, yeah, when I said that we know almost everything, there is to know, yeah, there is some gap left where we can, I mean, I'd love to discuss it with you later. I think we're like there are a few people in this room who are interested in this, like in this resolution of this discussion, and we're two of them. So yeah, let's talk about this later. But it almost, like, in many, yeah. But in a large sense, yes, for most parameter regimes, random linear codes do this. Okay. To work with random linear codes, there's one thing you need to know. So this is going to be the only thing you need to know about random linear codes. And this is, what's the probability that a random linear code contains a set of vectors? Okay. I have a set of vectors. What's the probability that a random linear code is going to contain it? So maybe I should first ask, I didn't write this here, but what's the probability that a plain random code is just like when you know, just a random subset. So what's the probability that a plain random code contains this set of vectors, v1 to vk? Assume that k is some constant, okay? Like think of k as being 100, not, I don't know, n. Okay? So take some small number of vectors. A plain random code contains a given vector with probability 2 to the minus 1 minus r times n. Okay, this is just the probability that a given vector is contained in a set. And in a plain random code, if you want to contain, you know, all of the set, you just multiply the exponent by the size of the set. So you put it k here. For a random linear code, because of the linearity, containing a bunch of vectors actually means containing the subspace spanned by them, right? It's the same thing. And the thing we care about is the dimension of the subspace that they span. So if these vectors are highly linearly dependent, then the probability of containing them is much larger because there's less, because we only care about the dimension. Okay, so this probability, the probability of containing a set is going to be, again, 2 to this minus 1 minus rn, which is just like this factor that depends on the rate of the code, times the dimension of the set spanned by v1 to vk. And this is really the only thing you need, like all the properties of random linear codes that we're going to talk about come from this observation. Okay. So let's talk about list decodability of a random linear code. Again, maybe I'll say again, right now we're talking about random linear codes, and our motivation eventually is going to be able to talk about other codes such as Reed-Solomon codes using what we're doing right now. But right now, in this specific part, let's assume that we don't have all the really nice results about list decodability of random linear codes that have been achieved throughout the last 20 or so years. We're just getting to this problem for the first time. And we want to show that a binary random linear code achieves the list decoding GV bound. Okay, and again, we don't need to know what's the list decoding GV bound. You just want to know that you want to show that it's list decodable of some good parameters. Okay. So, yeah, more precisely, again, this is what the list decoding GV bound says, but again, we want to show that it's list decodable of some good parameters. So how do you go about doing that? Here's one way to do it. Here's one notion that we need. This is the notion of witnesses. Okay? If a code is not list decodable, then there has to be some witness to this fact. How do I convince you that a code is not list decodable? I just need to show you the vectors that make it non-list decodable, right? If I want to show you that a vector is not that a code is like doesn't have good distance, I just need to show you two code words which are close to each other. If I want to convince you that it's not row L is decodable, I need to show you L plus 1 vectors that all lie in the same ball. Okay, so if there are L plus 1 vectors that lie within some radius row ball, we say that they are clustered or row clustered. Okay? And this tuple x1 to xl plus 1, we consider it a witness to the non-list decodability of a code C. So if I want to show that a random linear code is probably this decodable, I need there to be no witnesses. Like in the code movie. Okay. Okay. So how do I show? How can I try to show that a random linear code is list decodable, or that there are no witnesses? So a witness is a tuple of code words. I just told you what's the probability that a random linear code contains a given tuple of code words. So what I can try to do is compute the expectation of the number of witnesses, okay, the number of clustered tuples in a random linear code, and show that it goes to 0, that it's little o of 1. Okay, so it goes to 0. If I can show that, then I'm done. I showed that the random linear code is with high probability list decodable, just because of the Markov bound, right? Like the probability that there exists a witness is at least the expected number of witnesses. If the expected number goes to 0, then the probability of not being list decodable also goes to 0, and we're good. But now the question is this method tight? Okay? What do I mean by is this method tight? So this is actually something, okay, so this is actually something that came up through research. I was working with Venkat and Nick on this specific question in some guys. And we were trying to compute these expectations. And I asked myself, is it possible that we're going to miss something? Okay, like, is it possible that what we're doing, is it possible that random linear codes are less decodable with the parameters that we want? But by computing the expectations, we can show that, okay? That maybe just this expectation method is too weak because, I don't know, maybe the expected number of witnesses is large, but for some reason, the probability of there being a witness is still small, right? This can happen. If there are random variables where the expectation is large, but the probability of them being non-zero is actually very, very small. Okay? So what could this be the case? And yeah, and it turned out that, okay, I'll spell it for you. Yes, this is the case. The expectation method, as I describe it, just counting the expected number of witnesses, is not tight in general, or in some generality. So the first intuition was, yeah, maybe it's not tight. Why could it maybe be not tight? Because of an analogy from the world of random graphs, which I'm going to show you now. Okay. So here's a completely different question. So for those of you who don't know, a GNP random graph is a graph with n vertices where, okay, so there are n choose 2 possible edges. And each possible edge will occur with probability p. Okay? And the edges are independent from each other. Okay? So that's a model. It's called the Erdős-Rényi model for random graphs. And people have been studying these for much longer than they've been studying random linear codes. Well, yeah, not much longer, a bit longer. There's been more study of these, definitely. And one of the basic questions is, okay, let's choose some small graph h. Okay. What's the probability that a GNP graph contains an h? Or more specifically, how do I know, given h and given this p, whether the probability that GNP will contain a copy of h inside it goes to 0 or goes to 1? So what you can try to do is compute the expected number of h's inside G. So how many ways are there for h to occur in G? So the number of ways to put these 5 vertices inside the vertices of G is roughly n to the 5. And for each 5 vertices in G that were chosen, there are 7 edges, 1, 2, 3, 4, 5, 6, 7, that need to occur. So the probability, given such an embedding, a possible embedding of h into G, that this embedding will actually give you a copy of h is p to the 7. Okay, so this gives you the expected number of h's in G. However, the plot thickens, because you can all agree with me that in order for the graph G to contain an h, it must in particular contain this clique, which I call S. I mean, containing S is a is a necessary condition for containing H. And the number of S's in G, the expected number of H's of S's in G, so it's one vertex less and one edge less, so it's n to the 4 p to the 6. And the thing is, for some range of p, okay, when p is n to the alpha and alpha is within this range, then the expected, it's not, now you can easily see this for yourself, the expected number of H's is going to go to infinity, but the expected number of S's is going to go to 0. So we know that with high probability, G does not contain an S. Therefore, with high probability, it does not contain an H. However, the expected number of H's in G does go to infinity. So this is exactly an example of a random variable whose expectation goes to infinity, even though its probability of being positive is very, very small. Okay? So this is what happens. So the thing is that the expectation method, the analog of what we're trying to do for codes, turns out not to be tight for random graphs. Fortunately, we do know what is tight for random graphs. Yeah, okay, so this is just what I said, right? Almost surely there's not a single H can be found in G, even though in expectation many such subgraphs appear. Oh, maybe I'll say one more thing. It's just nice intuition. So why is it that there are many H's in expectation, even though probably not even a single one appears? Because the probability of having an S in the graph is an unlikely event. But if this unlikely event happens, then this copy of S is going to have many, leaves coming out of it. And each one of these gives you a copy of H. Okay, so in the unlikely event of containing an S, you're going to have many H's, not just one. Okay, and this is how we got to this strange phenomenon. Okay. So thankfully, there's a classic theorem about random graphs that tells us what is the case. Okay? So what we saw is that, okay, it's not enough to consider the expected number of H's. We also need to consider the expected number of S's, and of course, of any subgraph of H. And Bolobash in 1981 told us that this is enough. Okay? So if I want to know whether an H is going to be in my graph, I need to look at the expected number of H's and also the expected number of any subgraph of H. And if one of these expectations goes to 0, then I'm not going to have H's, obviously. But if all of these, and what Bolobash showed is that if all of these expectations go to infinity, they always go to either 0 or infinity. Okay, it's just like a very, very small point where they go to neither. So imagine it's always either 0 or infinity. Okay, so if all of these expectations go to infinity, then what this theorem says is that with high probability, we will have an H. Okay? And if you're interested to know how this is proven, it's a pretty straightforward proof. I think the hard part here is understanding what should be the right statement of the theorem. But once you have that, it really just comes from a second moment argument, nothing very spectacular. So that means that, okay, specifically for this graph H, the bottleneck comes from this S. Okay, so for every graph H, there is a subgraph which is like the one that needs P to be the largest in order for the expectation to be infinity. When you raise P, at some point each subgraph is going to go to infinity, and when the last one does, that's the bottleneck, then you're going to start having H's. Okay, so if you consider the probability of Gn P to contain an H, then really as you increase P, then you get this threshold here. Okay, like up to some point, the probability is 0, and then once you reach a point where the expected number of S's goes from 0 to infinity, then the probability becomes almost 1. Okay, that's enough about random graphs. Let's get back to codes. Okay, so now we're going to try and do the analog of this for random linear codes. So in order to do that, I need one more notation that's going to help me. Okay, so suppose I have a row clustered set, or actually any set of vectors. Okay? It's going to be very convenient to write sets of vectors as matrices. Okay, so if I have L plus 1 vectors, which would be a witness, like if they are in the codes and they are a bad witness, I'm going to write them as columns of this matrix. Okay, so this is a very tall and thin matrix because n goes to infinity, and this L plus 1, you can think of it as some constant. So it has L plus 1 columns. And these are just like x1 would be this, x2 would be this, xl plus 1 would be this. And I need the following observation. Okay, so I have the family of all the bad matrices. Okay, bad matrices are matrices that if they are in my code, then the code is not less decodable. I want to show that these are probably not in my code. So I just want to note that this family is close to row permutations. What does it mean? Right, I mean, if I switch a few coordinates here, if I switch rows, then obviously I'm not doing anything to the geometry of this set, right? The distances are still the same. It's just like it's equivalent to to permuting the coordinates of the code, which obviously does nothing to the geometry. So if some matrix is a witness, then permuting its rows is also going to give me a witness. But what does that mean? Suppose I give you a matrix and I ask you to tell me whether this matrix is a witness. Okay, whether the columns of this matrix together form a set that's contained in a ball. And I just told you that you don't need to know the exact rows. You only need to know how many of each row this matrix has. Because that's what being closed to row permutations means. It means that if you want to know whether the matrix belongs to the set, you only need to know the number of rows of each, like the number of occurrences of each sort of row, and then any way you arrange them, the rows in order, you're going to get a witness matrix.
Is that F2 to the L plus 1 or N?
Oh, sorry, yeah, that should be F to the L plus 1. This is a typo, and it's actually a very important typo. Thank you. Okay. And the thing is that once, instead of thinking, okay, so we can take this set of witness matrices, and instead of thinking about them as matrices, we're just going to think about their distributions. Okay, how many times does each row appear in such a matrix? And the thing is that this sort of projection, this projects the set of matrices into a much, much smaller space when I forget what's the matrix and I only remember its row distribution. Okay. So why is that? Because the row distribution is like how many rows, how many possible rows are there here? So if this is a binary matrix, then it has L plus 1 columns. So the number of each row can take one of 2 to the L plus 1 possible values because it's just a vector of length L plus 1. So if I want to know, if I want to remember a distribution, right? How many number between 0 and n, how many of each type of matrix, of each type of row I have, then obviously an upper bound for how many such distributions exist, right? Each distribution is a tuple of 2 to the L plus 1 numbers between 0 and n. Okay, there should be an n plus 1 here, but that's the basic. Okay, that's the sort of order of magnitude that we're talking about. And this number is very small. Okay, n to the 2 to the L. L is constant. So n to the 2 to the L plus 1 is a polynomial in n. And in everything we're going to do here, polynomial factors are completely negligible because, when we're talking about the number, say, the probability of containing a set, for example, in our code, we've seen that it's it's exponential in n. Everything else is exponential in n. So polynomials are completely negligible. Okay? So that means that when I think about the set of witnesses for non-list decodability, right? I have a set of bad witnesses. It's a family of matrices. I can divide this family. I can partition it according to distribution. Now, there's not that many distributions. And I just need, in order to show in general that there are no witnesses in the code, I just need to show that for each of these bad distributions, there's no matrices of that specific distribution in the code. And this is all, what I'm doing here is just trying to convince you that I can reduce everything to this problem. The problem is now going to be set some distribution, Okay, so maybe I'll go back anyway. So choose some distribution, some row distribution, a specific row distribution, but that belongs to this set of bad distributions. And all I care about is to show that for a given distribution, there are probably no matrices with that specific distribution in the random linear code, and then I can do that separately by a union bound, separately for each of the bad distributions. Okay, so we basically reduce the problem to thinking about a specific row distribution. Okay? So now the question is, the witnesses have a bunch of bad distributions, a bunch of witness distributions, and the question is, for a given one of these distributions, can we show that a random linear code with high probability does not contain any matrix with that specific row distribution? Where again, containing a matrix is containing its columns. Okay. And this is all. I remind you that we're talking about the expectation method. So we're still hoping to compute the expected number of matrices in the random linear code with this distribution tau, where tau is some bad distribution. And we hope to show that this number is small, and this way show that the code probably does not contain any matrix with this distribution tau. Okay? So I just want to show you that this is actually, like, for a given distribution tau, this is actually a very simple computation. Okay? Right, so let tau be some distribution over f2 to the L plus 1. And you want to know what's the expected number of tau distributed matrices, okay, in the code. So tau distributed matrices are matrices where the rows are distributed according to the specific tau that we've set. And we want to know what's the probability, how many matrices with this distribution we expect the code to contain their columns. Okay, so what's this number? It's the number of tau distributed matrices, okay, the number of matrices that have tau as a row distribution, times the probability for such a given matrix that its columns are contained in the code. Now, okay, this is some number that we know how to compute given tau. It's basically, if you think about it, it's just going to be 2 to the n times the entropy of this distribution tau. If you don't see that, then that's fine. If you do want to, I mean, you don't really need this is just like an, you don't need to understand where this came from, but I'll tell you anyway that, right, if you know the distribution of a matrix, then what you really need to do now to create a matrix with this distribution is you have n values distributed according to tau, and you need to somehow order them. And this, right, this is a multinomial variable, which is exactly approximated by this. And on the other hand, we also know what's the probability that this matrix belongs to that a given matrix with this, like after we did the ordering, what's the probability that a given matrix belongs to the code? It's going to be 2 to the minus n, 1 minus r at the dimension. We know that. And the dimension, know that it only depends on tau itself. Because if I know what's the row distribution, in particular, I know what rows are there here, then I can also determine the rank. Okay? So the point is that this gives me something that's really well defined because it depends only on tau. Okay? So I get this sort of expression here, 2 to the n times, this entropy of tau minus 1 minus r, the dimension of something with tau. And that's we don't really need to delve into this. But what you do need to know is that as you increase r, up to some point, this exponent here, this part of the exponent is going to be negative. So this expectation is going to be very close to 0, right? Because it's going to be 2 to the n times this negative number. And then once you cross the threshold where this part of the exponent becomes positive, then the expectation slowly is going to climb to infinity. This is in some weird scale. Okay, like this is very close to infinity, and this is very close to 0. Okay. So what does this computation give us for a given tau? So we know that as long as the rate is in this range, where the expectation is close to 0, then C almost surely does not contain tau. When I say contain tau, I mean almost surely does not contain a tau distributed matrix, okay? Because the expectation is small, and then the probability of containing at least one is mostly expectation. And then the question is this also true for, so this is going to be the analog of what we did for graphs, right? Like suppose now that the expected number of taus is large, the tau distributed matrix in the code is large, does this mean that C almost surely contains a copy of tau? And the answer is going to be, just as in the case of graphs, not necessarily. Okay? So what do we need? In the case of graphs, we also needed to consider the expected number of subgraphs of H. Okay, so if tau is analogous to some H, and we want to compute want to ask what's the probability that H appears in the graph, then what about subgraphs of H? How do we take them into account? What's going to be the analog, the correct analog of the subgraph, of taking the subgraph S of H and also considering its expected number of appearances in code? So here's what it is. Okay, so suppose that your code contains this tau distributed matrix A. Then, because of linearity, it also contains every linear combination of the columns of A, right? If I contain all the columns of A, I also contain all the linear combinations of A. So if I take A and multiply it by a matrix to the right, say that B is less than L plus 1, okay? Then I get a new matrix with B columns. And containing this AB is a necessary condition for containing A. So these sort of matrices AB for given matrices B, these are going to be the analogs of taking subgraphs. And the thing is that if I know B and I know tau, then I also know what's the probability of this matrix, right? Because how does a random row of this matrix, what does a random row of this matrix look like? A random row here is obtained by taking a random row of A, a uniform random row of A, and multiplying it by B. Okay? So if I know that A is distributed tau, then AB is distributed like, sample something from tau, say some vector z from tau, and multiply it on the right by B. So this is a new distribution that we call this tau B. So what we know now is that a necessary condition for the code to contain a tau distributed matrix is to also contain a tau B distributed matrix for every matrix B. And these are the subgraphs. Okay, so in order to contain a tau distributed matrix, a linear code must also contain a tau B distributed matrix. And now we have, this is the threshold theorem for random linear codes. So this says that if we want to know whether a random linear code is likely to contain a tau distributed matrix, then we need to look at all, we call them implied distributions, okay? All the distributions of the form tau B. And once the rate is large enough so that all of these go to infinity, then the code is likely to contain a tau distributed matrix, and until then, it's not. So this is exactly, and it's really the proof is really an analog to the proof of the theorem about random graphs. It's also obtained using second order methods.
Quick question. So
Yes.
it also says that when this doesn't happen, it will not contain, right?
Yeah. So the other direction is easy, right? Yeah. So it's an if and only if. One direction is easy. If I didn't say it explicitly, right? But if the expected number of tau B distributed matrices is small, then the probability of containing a tau B distributed matrix is small. But containing a tau B distributed matrix is necessary for containing a tau distributed matrix. So that's probability is also small. So that's just by a first moment method, this is immediate. The other direction, that if all the tau B's have large expectation, then you're likely to contain tau, that's not obvious. It requires this theorem, which again is not very hard to prove once you know what you're trying to prove.
So one other question is probably I'm not able to follow that mistakes in my head. So you already are taking this to see that this set of vectors contained. So you are basically looking at the dimension of this set.
Mm-hmm.
You have this 2 to the power minus n times the dimension of
Yes.
So if the space scanned by those vector is contained, wouldn't all of this tau, like this b, like how do you get this b? It's basically multiplying that set by.
So B is usually B, you should think of B as being a matrix of, like, if you, B is of dimensions L plus 1 times B, you think of this little b as being less than L plus 1. Okay, so you project onto a smaller subspace.
Okay, so it's a small.
Yeah. For this to make sense, you like this is me. This doesn't give you anything. If say B is a regular matrix, you need to project into a smaller subspace, and then just like with the subgraphs, you also in a sense projected into like a part of the original graph. So it's the same. Okay, and this allows us to say something about, like, I'm reminding you that the original motivation for studying all of this was during research that was intended to to explore list decodability of random linear codes. I was concerned that maybe computing the expectations of the taus is not enough, and then we have this corollary that tells us what is enough. Okay, so what can we do to show that the random linear code is list decodable with some parameters? We need to show that for every distribution, tau, every bad distribution, every witness distribution, either the expected number of tau distributed matrices in C, it goes to 0, but that's not the only thing we can do. We're also allowed to take some B and show that the expected number of tau B's in the random linear code goes to 0. And what we've proven is that this is a complete method. Okay, this method is complete in the sense that if I restrict myself to, for every tau, finding such a B, then I'm not losing anything. Anything that can be proven about random linear codes can be proven this way. Okay, this is the corollary. And this corollary also gives us, again, it's a threshold thing, right? Because it means that for a given tau, for any tau, there is some B, which is the bottleneck. Just 1 second, I'll finish it. There is some B, which gives us the bottleneck. That is like the this is like the B for which, like, tau B requires R to be the largest in order for the expectation to go to infinity. And then you start containing a tau once R reaches the bottleneck, and then it falls very quickly. The probability of being less decodable, the probability of containing tau goes very quickly from 0 to 1, and the probability of being least decodable goes very quickly from 1 to 0 because you're going to contain a tau. Yes.
You've written this statement just for FQ, but like, does all of this also happen in?
Yeah, all of this holds for FQ with some reservations. So these reservations are going to be a key part of the next talks. Okay, you asked, so I'll say right now something about this. For Q constant, any constant Q, this holds just the same. The problem starts when, for example, you want to talk about the regime of, say, Reed-Solomon codes, where Q is like N. And one of the places where this fails for large Q is that now you have many. Okay, so recall that the number of bad distributions was 2, or sorry, it was like N. It was N to the 2 to the L. Now, in general, it's going to be N to the Q to the L. And now, if Q is 2, then you're here, you're good. It's constant. If Q is 3, you're still good. If Q is N, as it is in Reed-Solomon codes, then this is N to the N to the L, and this is not so funny anymore. You can't do a union bound over all the bad distributions, so you need to be much more careful in how you approach that. So that's why for Q being less than, I guess, anything that's like polylogarithmic, you need to be less than polylogarithmic in N, and then you're still okay. But beyond that, it's not good. Okay. But yeah, I mean, okay, maybe I'll Okay. So just like what? Okay, so we proved this threshold theorem, and what are the takeaways so far? So the less decodability of random linear code can be explained by expectations. Okay, this expectation method that we've shown, when we allow ourselves to also multiply, not just consider the bad distributions tau themselves, but also these tau b's, then this is a complete method. Okay, so anything about this decodability of random linear codes can be explained if I just like you know everything if I just tell you these expectations of the tau and all the tau b's. Okay? They're just like you just need to know these terms basically. But this holds for more just list decodability, right? Because what did we really need from this? Like, we didn't know that in doing any of this, we didn't really delve into the semantics of list decodability. We needed two things from list decodability. One is that there are short witnesses, right? If I want to show you that the code is not list decodable, I just need to show you a small number of code words that that witnesses this fact, that certifies this fact. And the second thing is this symmetry to row permutations of these witnesses. Okay? So basically a property that doesn't care about the names of the coordinates in the code. Okay? And any such property, the same sort of method would work. You can take this property and consider your witnesses now have like your witnesses are now characterized by their distributions. So you have a set of witness distributions, and then you can do the same sort of thing we did here, just for a different set of witness distributions. So for example, list recoverability can also be characterized this way. And for this, we really need the version of the threshold theorem that works not for Q, but for larger Q. Okay? But again, this only takes us up to any constant Q, not for Q going to n. But for any constant Q, this still works. So we can, for example, characterize the list recoverability properties of random linear codes this way. And in general, any property that's monotone in the sense that as you increase the code, the property can only, like if you add more code words, you can only hurt yourself, right? That's monotonicity. That's increasing monotonicity of the property. Locality, you have short witnesses, and the symmetry to row permutation. So any property that has, any code property that has that, this method applies to it. Okay, that's nice. But that's somehow not interesting. I mean, I like it very much. I think this is very interesting, but somehow I feel that this is not interesting enough for me to be talking to you about this here. So what else did we gain? So, okay, we know that reasoning about list decodability of random linear codes via expectations is a complete method. But what is this good for? Well, in fact, as a way of reasoning about random linear codes, it's not good for that much. And this is, first, because it doesn't actually tell us how to prove that, I mean, it tells us that a certain method that we already have for proving list decodability of random linear codes is in fact complete, but it doesn't actually, like, we already had the method, we just didn't know that it's complete. Now we know, we're reassured that's good. But also, there's a very long line of works that already showed us that random linear codes achieve the list decoding GV bound. So this is actually a pretty known fact by now. Again, up to some objections by Omar, but almost, but this is almost a completely known fact for any set of parameters. So, okay, so I actually showed you that a certain method for proving something that's already known to be true by other methods is complete. Okay. But now here's the thing. We have, actually, I'm surprised by, we're going to finish even in a good place to finish. Okay. So, yeah. So now, all of these results that already exist, which were proven by many people, some of them are in this room, about list decodability of random linear codes, in fact, tell us something about expectations, right? Because if I know for some other contrived reasons that random linear code achieves the GV bound, and the list decoding GV bound, then that means that for every witness distribution, there exists some matrix B such that the expected number of tau b's in the random linear code is small. And this is something I learned now for the threshold theorem. I didn't know that just from these proofs, because these proofs worked in completely different ways, but they all tell me this fact about these matrices, about these expectations of the tau b's. Okay. So how do I use this fact? I can now use this to talk about other random ensembles of codes. And I'm actually going to show that many other codes also achieve the same list decoding properties of random linear codes. So for this, I need a definition. I'm going to define when a random code ensemble. Just think of a random code, okay? Like if a random code that's with some distributed somehow, okay, taken from some other distribution, not a random linear code, but some other distribution of codes. So we say that this random code is locally similar to a random linear code. If you remember the only thing you need to know about random linear codes, if this other code C approximately satisfies this same thing, okay, that the probability of containing a small set is roughly the same as in a random linear code. Any code that does that, we say that it is locally similar to a random linear code. And what we can now prove is that there do exist locally similar, there do exist codes that satisfy this definition. We're going to talk about it later. But right now, I can tell you that every code satisfying this definition, every code that's locally similar to a random linear code, also takes the same list decodability properties that were gained with a lot of work about random linear codes. So this is the only slide where I actually show a proof because it's important. I'm going to go over it quickly, but it is going to be written for you. So yeah, so the theorem is that if a code C is locally similar to a random linear code, then, for example, it achieves the list decoding GV bound with high probability. Okay, how do we prove this? So let D be a random linear code. And we know from previous works that D with high probability, achieves the list decoding GV bound. Okay, so take some rho and L, and we want to show that every rho and L for which D is list decodable, our code C, the locally similar code, is also going to be list decodable with these parameters. Okay. So let tau be some witness distribution. Okay, so tau is going to be a row cluster distribution. So we know that D, the random linear code, is list decodable, is probably list decodable, so it's unlikely to contain tau. By the threshold theorem, how can it be unlikely to contain tau? There must be some B such that the expected number of tau B distributed matrices goes to 0. But because of local similarity, what's the expected number of tau B distributed matrices in C? It's the number of tau B distributed matrices times the probability for each matrix that it's contained in C. But this is the same as the probability that this matrix is contained in D, because these are small sets of vectors, and local similarity tells us that this is going to be the same term here. But so this is exactly also the expected number of tau B distributed matrices in D. Okay, it's the same thing. Okay, so local similarity of C to random linear codes means that the expected number of matrices with some given distribution is going to be the same. So this distribution goes to 0, and then that means that this distribution also goes to 0. But if the expected number of tau B distributed matrices in C goes to 0, then C is unlikely to contain a tau B distributed matrix, because the expected number of such matrices goes to 0. But then it's also unlikely to contain tau, because containing tau B is necessary for containing tau. Okay, so this is like a generic reduction now. In order to show that a code is as list decodable as a random linear code, I just need to show local similarity.
Sorry,
Yes.
it's a fixed code, right?
No, C is a random code. A random code, but by some other code distribution. In a second, we're actually going to be talking about two certain distributions for which this holds. And Okay, and this again is going to work also, for example, for list recovery. So if we have a cool result about list recoverability of random linear codes, when it immediately transfers to C, to this other random code as well. And even if in the future we discover some new, better results about list recoverability of random linear codes, we're also going to transfer to C immediately. Like it's this, it's grandfathered in, which is cool.
So maybe one question. So this approximately equal probability, you allow some epsilon in the exponent. That's
It's this would be like -1 minus R plus epsilon.
plus epsilon. Yes.
Okay. So here's a technique using Mary's hammer. How do I show that a code achieves the list decoding GV bound? So I start from a random code ensemble of my choice. I show that it is locally similar to a random linear code, and then I use the theorem I just showed to conclude that it achieves the list decoding GV bound. And of course, the tough part is how do I show that a certain code is locally similar to a random linear code? So this was actually done successfully for 2 code ensembles. One is the ensemble of random LDPC codes, known as Gallagher's ensemble. So these are codes where the parity check matrix is essentially a random sparse matrix. And this is the first work that's the threshold theory appeared in with Nick Resch, Nogel and Savi, Sheshel Seals and Mary. And there, we didn't use these terms exactly, but essentially we show that these random sparse matrices are parity check matrices for codes which are locally similar to random linear codes. And then we conclude for list decodability. And again, also that, for example, there is list recoverable as a random linear code. And later, this was also done for a set of ensembles, randomly punctured low bias codes. Okay, so you start from a code of low bias. A code of low bias is, so in the binary case, just think of a code where the weights, a code that has good distance, like the weights are close to 1/2, but also from above, like the weights cannot they're not too small, but they're also not too large. We're between like a 1/2 minus epsilon and 1/2 plus epsilon or something. Okay. You take such a code and you apply random puncturing to it, which is something we're going to be talking about tomorrow. And this gives you some random code that's locally similar to random linear code. So we've shown that every code that can be described this way is as list decodable as a random linear code, so it achieves list decoding GV. Okay, a few words about what we're going to do next. So one thing is we're going to explore this, okay, so this result. And then we're going to be talking about the bad here. And some of the bad is really that, okay, we want to eventually be talking about list decodability of Reed-Solomon codes. And the problem, again, is that the method I showed you right now is not enough to do that because it doesn't work when Q is large. So we'll be exploring why it doesn't work, like trying to fine-tune more precisely what's the problem for the large Q case, and then we'll see ways to overcome that. Okay, I think that's it for now. Thank you.
Excellent talk and leaving us in suspense tomorrow. Any questions? Yeah.
Can you quickly comment on how you apply the threshold theorem for just random linear codes?
Sorry, how do you?
You want to show for every tau there's some B, like,
Yeah.
How do you make that happen?
Are you talking about how do you actually use that to? Okay, so the idea in theory would be the following, right? So for example, consider that you're really trying to show that that a random linear code is list decodable. Okay? So you need to think about all the possible taus. Now, one tau that's easy to, that's like the obvious one, and it's easy to show that that there you get like the expectation goes to 0, is just think about L+1 vectors with no linear dependence between them that somehow all fall into the same ball. And this is really easy to compute. Now, the problems start when you need to also consider when you do have linear dependencies. So for example, the other extreme case is think about you have L+1 vectors, but the dimension is just log of L+1. Okay, so it's like you have a small Hadamard code, or right, like all the or something like that, and then you somehow need to go over all the possible, like you need to see which distributions with these which distributions of rows that have these linear dependencies between them give you like all fall into a row-shaped ball, and you need into a radius row ball, and you need to somehow pick like the worst case one would be the one that has the largest entropy of all of these distributions, right? So and you go into entropy maximization problems. Of course, it's also possible that someone there's a distribution with smaller entropy, that like the distribution with the largest entropy versus some B that reduces it to much smaller entropy, but so it's not clear that you always that the adversary you would always want the largest entropy one because of there's also these B's involved. I think that maybe gives you a feeling about why this is still a tough problem, even when you have this theorem, like even this method. Like, I mean, eventually, the ways for which these results for random linear codes were eventually obtained was not through this method, and I think there's a reason for that. Like using this method to actually argue about random linear codes is hard.
One more question there, and then maybe dip out for lunch. Do you have a question? No? Okay. Yeah. Quick question? Right? Okay.
Maybe give a quick comment, actually, just to follow up on what Jonathan was saying. I think, I've worked a bit about actually using this characterization to compute the threshold rate. And I think for like binary codes, we can do it for like list of 3 decoding and list of 4 decoding. That's still already too hard to solve, just because already there you have to like look at, sets of size 5 and like all the different ways you can project them down, and that just becomes too many combinatorial things to keep track of, at least for me. So that's already kind of where we're stuck.
Maybe I'll say one more thing about this is that actually, when you let Q be large, then okay, this method specifically doesn't work for this for Q large. But actually, when you allow Q to be large and take like the analog of this method that we're going to talk about tomorrow that does work, then it's actually easier. Because for large Q, because entropy is much easier to work with. The query entropy function is just linear, so it's and that makes the things more easier to handle.
So I gather that you don't get a completely new proof and you can trash the old results, but you have to.
No. You need it's the opposite. You need the old results, and then this proof gives you the possibility to reduce them to reduce from other codes to random linear codes.
Maybe I'll ask a question based on Nick's comment. Is there a proof using this method only that shows random linear codes do it, or is it explode?
So there is one for for large Q. It's also it's not on the archive yet. It will be on archive soon. There is one for large.
Isn't it possible to adapt like the GHK argument? Didn't we convince her?
Yeah, I think the Guruswamy-Hastad Koparty proof is can essentially be seen as using this method. Well,
yeah, if you just use their ideas.
Also, the old Pinsker-Ziablov argument is also can also be seen as using this method, but in a very crude way.
And there are also some for small lists.
Yeah, exactly. And then it's just counting and doing everything by hand. Yeah. At least I have no more clever ideas at this point.
Oh, we do have something for
No. All right. So thanks again, and thank you. So we meet again at 2 o'clock for back-to-back.